Hello, I'm Phi Myers. Welcome to the third and final module on tank corrosion. Take a look at this for a second. Metabolic rate is how fast complex organic compounds are converted to energy to supply all life with its metabolic requirements. I'd like you to look at the variables on the left and then some variable effects and interactions on the right and determine how you would predict the metabolic rate for any animal, whatever, from a single cell to an elephant. Give up? It turns out that predicting the myriad variables I just showed would be a fool's errand because it would be like trying to roll a boulder up to the top of an infinitely tall mountain. But Kleber's law is very simple and accomplishes this task with the power law shown in red. Amazingly, it works well throughout the animal kingdom from amoeba to elephants. Why am I talking about this? It is because tank soil-side corrosion is similarly complex, and attempting to predict corrosion rates for tank bottoms should be approached using a simplified model such as a power law model. Back on topic. Corrosion can be measured at any time for all tank components except for the tank bottom. That is why we are focusing on tank bottom corrosion during this talk. Getting access to the tank bottom requires that the tank be cleaned and gas-freed so that internal entry into the tank can be made to assess the state of corrosion as well as the internal condition of the tank. Typical corrosion mitigations are coatings and slope bottoms. The window of opportunity for bottom corrosion measurements piggybacks off of the tank internal inspections, which only occur every 10 to 20 years. Unfortunately, no serious public domain work has been done on corrosion rate prediction for tank bottoms. I doubt that any company has done sufficient work in data collection and analysis either. In the data sets I have reviewed for several major integrated oil companies, they all had serious flaws making predictive analytics for corrosion impossible or inaccurate at best. Earlier I said that tank bottom corrosion was complex. You will often see or hear a claim that corrosion can be predicted with a table like the one at the top left. Unfortunately, what is not mentioned is that the variables, and there are many of them for tank corrosion, such as those to the right, they have interactions. To explain this, consider the enjoyment of eating a hot dog. Does a condiment increase enjoyment? In the example of the hot dog versus ice cream, the obvious answer is it depends. Enjoyment goes up if chocolate syrup is added to ice cream, but it goes down if added to a hot dog. Whereas enjoyment goes up if mustard is added to a hot dog, but goes down if it is added to ice cream. The effect of these variables for condiments is called variable or factor interaction, and this is the simplest possible case. Imagine all of the interactions taking place for the variables in the flowchart where there can be 3 and even 4-way interactions. No wonder it's nearly impossible to predict tank bottom corrosion. I definitely am not saying throw up your hands and give up. Much more can be done. What we do know about tank bottom corrosion comes from NIST, where there was and is interest in buried pipelines, power generation, and infrastructure where steel is in contact with the environment. Early on, it was recognized that steel corrosion follows a power law, as shown. The corrosion rate slows down with time because the ionic flow path becomes even more difficult as a result of corrosion products that impede the ion flow. At this point, I remind you of Kleber's law, and that it too was a power law. Of course, the parameters are different, but a simple power law works for corrosion too. However, today, and rightly so, the linear corrosion rate model is used. Even though it is slightly less accurate than the power law, it's much simpler to work with. So let's dive into corrosion modeling now. What does tank bottom corrosion data look like? Here is data from a major integrated oil company where the internal or product side corrosion rate for 33 finished fuel tanks in 5 refineries was investigated. In total, there were 30 gasoline, 8 jet, and 4 other tanks. You can see from the table that 2 were in one refinery, 5 in another, 12 in a third, 10 in a fourth, and 4 in a fifth. At the lower right, you see a box plot for this data. A box plot shows the interquartile ranges. The heavy line is the median. The lower 25th percentile for this plot is nearly 0, and the 75th percentile is just above 10 mpy. There was one tank that had a corrosion rate of around 25 mpy. Unfortunately, in this study, they failed to state whether the tanks were coated and how long the tank was in service when the corrosion rate measurements were made. Now let's look at soil side corrosion rates for these same tanks. The two plots are just different representations of the same data. Every data point is shown in the left plot, which is called, not surprisingly, a dot plot. The box plot on the right shows the 25th percentile is now about 5 or 6 mils per year, and the 75th percentile is around 12 mpy. There are also more outliers, and these have higher corrosion rates than the product side. For finished fuel tanks in refineries, it is clear that soil side corrosion is more aggressive than product side corrosion. One important aspect of the data was that it came from 5 different sites, and you would expect they differ in terms of corrosion rate. Although data should never be tossed without a good reason, in this case one of the refineries was on such a muddy soil in a marine environment and with mostly heated tanks that it was thought not to represent typical corrosion rate processes for finished fuel tanks in refineries, and so was thrown out. The histogram at the right shows that most soil side corrosion is less than 10 mpy, but the long tail also shows that it's possible to have very high corrosion rates occasionally. I want to mention the El Segundo bottom. This is a double bottom tank that uses a concrete spacer and not a sand spacer, which is why it deserves its own special name. Here's a picture of one. The original bottom is covered by this gravel. This new bottom, or the current effective bottom, is shown here. This is a telltale port, and you can see some water has been poured out of this interstice. Concrete is alkaline, and steel is known to have reduced corrosion rates when in contact with the concrete. Based on a study at the El Segundo refinery, the corrosion rates were substantially less than those for a typical single bottom tank. Every tank at this refinery now has an El Segundo bottom, and the corrosion rates are much less than for single bottom tanks. The red line in both plots shows the El Segundo tank bottom probability density and distribution. The blue line is for the previously installed single bottom tanks. In our quest for understanding tank bottom corrosion, we came across systematic studies by NBS, which was formerly the U.S. National Bureau of Standards, and is now NIST, or the National Institute of Standards and Technology. In the old days, it was not known if cross-country pipelines should be insulated, so a long-term study between 1922 and 1939 was conducted for this purpose. Samples of pipe were buried in 47 sites throughout the U.S. Specimens were recovered, and every 2 years, some of them were dug up to periods as long as 17 years. There were 3 alloys used. At the time of the study, the practice of statistics was in its infancy compared to what we know how to do today. The study was looked at again using modern knowledge of statistics at the request of DOT. Dr. Ricker published his findings in 2010. I had the privilege of discussing his study in detail with him in 2010. Looks like a government operation out of the 40s or 50s, doesn't it? This is where NIST exhumed pipe samples which were tested and analyzed for corrosion. Unfortunately, I doubt a serious study like this for tank corrosion will ever be conducted again. The black dots show the burial sites spread throughout the U.S. with soil types indicated by color. Here is a corrosion pit depth versus years in service. Notice how smeared out the corrosion depth is. You can see that the trend is really somewhat nonlinear, because for rates under 4 years of burial, the rate is increasing faster than it is beyond that point. These are best fit regression lines. The corrosion depth data have been put on the log scale, which makes the data appear to be linear. In fact, the linear fit to this log data is quite good. You can see that each alloy has its own regression line, meaning that the alloy had an impact on how corrosion was occurring. This is the same plot showing the pit depth on a linear scale where you can see the power law causing a slowdown in corrosion. The copper steel corroded faster than the other two alloys, which corroded at virtually the same rate. This plot shows the maximum corrosion penetration rate, and clearly the resistivity forms a trend line, a regression line, where increased resistivity reduces the rate of corrosion as you would expect. But don't take this too seriously, because there is variable interaction with other variables such as the types of ions in the environment or the presence of oxygen, which we showed can have a large effect on how variables behave when they are combined. We studied the data from a large tank facility operator, which we will refer to as Petroleum Storage Facility Operator, or PSFO. Note that the data are sparse, whereas the data for mouse clicks can be collected free by the millions per minute by companies like Facebook. Each data point collected for tanks represents about $1 million in tank cleaning, and outage costs occurs only once every 10 to 20 years, and yet still gets screwed up because people do not have or follow a rigorous data collection protocol for the express purpose of understanding and predicting tank corrosion rates. Covariates such as soil chemistry or the use of coatings is often missing, which makes the data analysis process less certain and potentially misleading. At PEMY, we combine the NIST data with the PSFO data. The black open circles are the NIST data. The black triangles are where the corrosion penetrated the wall thickness. Similarly, for the PSFO data, the open red squares are the pit depth, and the solid red triangles are where the bottom was penetrated by corrosion. Because it is not known when the penetration actually occurred, it has to be treated using different statistical methods. This kind of data is called censored data. We fit a power law to the combined data set. As expected, it is close to the square root of time, where depth is equal to a constant times time in years to the 0.41 power. Actuaries develop actual human survival probabilities by age for the purpose of insurance, healthcare, and many other purposes. They use cohort data, which is a group of 100,000 people born in a certain year, and then track them until there are no survivors. There's plenty of data for human mortality because it helps insurers to stay profitable. But for tanks, the data is sparse and scant. Therefore, statistical methods must be used to establish probable lifetimes, where life is defined as a period prior to corrosion penetration of the tank bottom. Although we did not invent the idea of the gamma diffusion process for corrosion analysis, we did apply it to the sparse tank data that we had, and I will show you that now. We first have to have an understanding of a random process, and what better way is there than the so-called drunkard's walk? A man staggers randomly in different directions. Now, while you can have a 1D or 2D or 3D random walk, we'll just focus on a 1D random walk for tank corrosion. But let's say that he has an equal probability of stepping to the left or to the right. If he had to walk a highway line, the plot shows how he would tend to wander to and away from the line. Because the probability of moving to the left or right is equal, the long-term average of all steps is 0. It's on the line. But let's change up the process a little to mimic corrosion depth. Let the drunkard only be able to take forward steps or positive steps. Corrosion only increases, it never decreases, hence the step is always positive. Let's say the distance a drunkard steps forward is governed by the gamma probability distribution. I'll show you what that density looks like in a second. Finally, the probability of distance of each step forward is unchanging with time. Putting this all together, we get the next slide. Unlike the first scenario where the drunkard walk had a mean value of 0, the mean value is shown by the red line. Corrosion is ever increasing, and the red line shows the average value, which follows the power law, but we treat each time increment as a random step, where each step has a gamma probability density shown by the humped curve. Notice that it's not a symmetric curve. The gamma probability density is non-negative, so no steps reverse direction. Just like corrosion, the direction of corrosion is always positive. The gamma density just shows the likelihood of the jump size in corrosion depth at the next time increment. Part of the analysis is to figure out the most likely parameters for the gamma density, which are called the shape and scale parameters. I won't get into that now, as I'd probably put you to sleep. This is just another way to look at the jumps in corrosion using the gamma process model. The total corrosion growth is just the sum of the independent increments. Because we are dealing with a stochastic or random process, if we were able to start the clock from zero over and over as many times as we like, we would get a series of lines representing what I will call corrosion histories. Each gray line represents a possible corrosion history, so you can see that some will result in larger corrosion growth than others. This is the essence of a random process. The cool thing is that we can count the number of corrosion histories which penetrate the 250 mil thickness dotted line, which is the number of corrosion histories which have caused penetration failure. When this is divided by the total number of corrosion histories, we get the probability that the corrosion will fail the bottom as a function of time in years. The noise around the mean value of the pit depth is shown by the gamma density. The gray below the 250 mil penetration depth is the probability of no penetration given the time in service. So at time t equals 0, we have 100% survival rate. At 60 years, we have a 19.8% survival rate. Notice at 20 years, the survival rate is over 95%. This is the motivation for RBI. By design, the internal inspection intervals prescribed by API 653 are necessarily going to be conservative, but the standard allows savvy operators to use probabilistic methods to set internal inspection. As an alternative to the table is a survival curve shown here. If we want to set our acceptable survival probability to 90%, we can just follow the red line from 0.9 to the time axis, and we get the P90 of 38 years. So it takes 38 years before their failure probability has reached 10%, and the survival probability will increase below 90%. I wanted to show you what a corrosion modeling app might look like. Basic data for the control and candidate tanks are input, and the output is a survival function, output for the 85th, 90th, and 95th percentiles, listing when the tank should be taken out to meet the survival criteria that are specified. Note that I recommend that a survival criteria for operating the tank be no higher than 90%, but that's just an opinion. As a point of reference, medical statistics typically use a 95% level as a criterion for effectiveness of a treatment. The prototype app can output the lower probable error, which is the 75th percentile, that the true curve is above the dotted line. The solid line, of course, is the survival curve. I have outlined some of the standard methods of estimating corrosion from data, but until we get data in a proper form, RBI and similar service will not be able to work properly. This is one of the reasons so many companies struggle with RBI as well. This is in addition to a proliferation of black box methods that are questionable. It is no wonder that not only do regulators, but industry itself does not trust these methods fully. We've talked about corrosion mitigation factors, so I won't belabor this other than to say many of these factors must be systematically tracked in order to use corrosion data to predict corrosion. Other factors that influence tank corrosion are listed here, and they as well should be tracked in a corrosion rate database. There are many other issues related to how corrosion is actually measured, and we won't go into these now as they have been covered by other speakers. The top-level message of this talk is that if the tank industry ever wants to move into the age of data and AI, it will have to conduct studies that are properly formulated, collecting the right kinds of data, and using sound data analytic methods so that we can optimize the internal inspection frequency. This is not just about costs. Unnecessary and too frequent tank openings cause significant liquid and gas emissions. Not inspecting tanks frequently enough has the potential for tank bottom leaks. The only way to optimize this is to have the data, understand it, and analyze it so it can tell us how to set the tank inspection intervals. I don't have much hope that API or NACE has the will to get the minimum data set so that the tank internal inspection intervals can be optimized. This is because the effort is a long-term effort that takes a committee of experts in tanks, corrosion, and data analysis to set up the protocols for the data collection and persist for years in collecting the data so that we do have a minimum data set. I hope there are those of you out there who can make it happen in spite of the challenges. If there are reactions or questions, now is the time. Otherwise, I'd like to thank you.